A number of American high-performance air and space designs were at least partly inspired by World War II concepts from Nazi Germany. Northrop's tailless swept-wing X-4 used a semi-flying wing design which built upon not only Jack Northrop's earlier designs, but also German work in the 1920s and 1930s by Alexander Lippisch and the Horten brothers. Its more immediate inspiration, Britain's DH-108 jet, bore striking similarity to the wartime Messerschmitt Me-163 rocket fighter. Results from the X-4 flight test program influenced a number of future designs. The X-5, with its variable geometry or swing wings, was based on the wartime Messerschmitt P1101 prototype. That innovation saw fruition in the 1960s with the F-111 and later with the F-14 Tomcat fighter, B-1 Lancer bomber, Europe's Tornado multi-role fighter, and most prolifically of all, in the USSR with numerous MiG, Sukhoi, and Tupolev attack bomber designs. America's space program was kick-started by German wartime scientists who had worked on Nazi rocket projects such as the V-2 and Me-163 and who were imported to the USA after the war through Project Paperclip. Another German wartime idea, from the fertile minds of Dr. Eugen Sanger and his future wife, Dr. Irene Brett, seemed like pure science fiction at the time, but laid the groundwork for America's post-war lifting body aerospace planes. Sanger and Brett's Antipodon Vergleiter, or antipodal long-range glider, codenamed Silbervogel, Silverbird, was a design proposal submitted for Germany's America Bomber project. With a length of 28 meters and a 90-ton fuel load, it was to be launched from a rocket sled riding a 3-kilometer rail. Entering a rocket-powered 30-degree climb, the bomber was to reach a speed of 6 kilometers per second, more than half the Earth's escape velocity. Its rocket fuel expended, it would skip, like a pebble on water, on the atmosphere after descending from 145-kilometer altitude. Using that technique, it was expected to travel 24,000 kilometers to the other side of the world, the Antipodes, and along the way, bomber targets such as New York, before atmospheric re-entry and landing in Japanese-held Pacific territory for reuse. Fantastic as the scheme was, considering the level of technology of the era, the craft's weapons payload would not have justified the effort and resources expended. Even if its bomb could be guided to a target, its efficiency would have been inferior to that of the V-2 rocket. Itself a space bomb of sorts, the V-2 could reach an altitude of 175 kilometers and guide a 1-ton warhead towards a target at hypersonic speed, though not accurately. Sanger and Brett's antipodal bomber proposal was captured by US forces at war's end and sparked some interest in America when it resurfaced a few years later. The rail launch technique, used at a smaller scale in 1944-45 for launching V-1 flying bombs, did at least appear in science fiction on the silver screen. In the 1951 film, When Worlds Collide, for example, it was used to launch the huge Space Ark rocket, which saved mankind from destruction. Among the German rocket scientists brought to America under Project Paperclip were Kraft Erika and Dr. Walter Dornberger. Erika had published work on spaceflight to Mars, and Dornberger was the wartime major general who had coordinated the V-2 program, and famously, the man to whom Hitler apologized for dismissing his military rocketry proposals. Working for Bell Aircraft Corporation in New York in 1952, Dornberger and Erika submitted a design for a glide bomber. Less ambitious than Sanger and Brett's proposal, it would be launched by two-stage rocket to an altitude of 100,000 feet, reach Mach 4, and traverse about 5,000 kilometers. Although official reaction to the space bomber concept was lukewarm, the USAF Air Research and Development Command, ARDC, at Edwards Air Force Base, California, saw the idea's potential for reconnaissance. In 1954, ARDC began backing research into hypersonic suborbital vehicles, and 3 years later instituted a program called Dyna-Soar for dynamic soaring. The program's aim was to develop a manned hypersonic test vehicle to investigate the flight regime beyond that of the X-15, which was then in development. The goal of the three-step Dyna-Soar program would be an orbital vehicle, the X-20, for military reconnaissance with bombardment as an additional option. Proposals were sought from industry, Lockheed, Republic, and North American devised plans for an orbital satelloid. Douglas, McDonnell, Convair, Martin, Bell, Northrop, and Boeing proposed a maneuverable manned glider boosted to 300,000 feet altitude and a speed of 28,000 kilometers per hour. The glider could reach the other side of the globe, while suborbital and as an aerodynamic design, return to land conventionally for reuse. The National Advisory Committee for Aeronautics, NACA, agreed to provide technical advice to the Air Force. By November 1958, when an agreement was signed, NACA had become the National Aeronautics and Space Administration, NASA. The Dyna-Soar development phase called for airdrop tests from a B-52 mothership, designated MB-52B, to begin in 1962. Early tests were to include acceleration to supersonic speed using a thiacal solid-fuel rocket. Manned suborbital launch tests were to follow, and finally the first manned global flight would be made in 1963. An offensive weapons system was to be operational by 1967. The X-20 was planned to be launched on top of a Titan IIIC rocket, reach 320,000 feet 9 minutes after launch, and enter a 24,000-kilometer trajectory. It would deliver a half-ton weapons payload from space, re-enter the atmosphere, and 105 minutes after launch, touch down with a landing speed of 280 kilometers per hour. Designed to withstand the temperatures and forces associated with atmospheric re-entry, the X-20 was to be constructed of exotic materials. The primary metal was a nickel alloy called Rene 41, also used for the shingles covering the Mercury space capsule. The underside heat shield and wing leading edges would be of molybdenum and the nose cone of graphite with zirconia rods. The gap between the outer heat shell and the internal shell was to be water-filled to dissipate heat by evaporation. Heat-exposed surfaces would be covered in a ceramic material, later used for heat tiles on NASA's space shuttle. Attitude control in space was to be accomplished with nose and tail-mounted thrusters, and, following re-entry, hydraulically actuated elevons would control roll and pitch. The pilot's control stick, a small side-mounted joystick for high-G situations, was adopted later on the F-16 fighter and some modern airliners. The windshield windows, resembling those used on the space shuttle, were covered with an alloy heat shield, which would be jettisoned after re-entry. The X-20 project progressed far enough for 5 USAF pilots and 1 from NASA to be selected to fly it. However, after a full-scale mock-up had been built, funding constraints and delays moved the scheduled date for its first piloted launch back by 3 years, to 1966, and the program was finally cancelled before the partly built X-20 had flown. Nevertheless, its legacy lived on, notably in the Space Shuttle program and in Boeing's later X-40 Space Maneuver Vehicle and X-37 Orbital Test Vehicle for U.S. Space Force. To quote Jay Miller in his book The X-Planes,
in particular, fundamental re-entry heating dynamics, technology generated by the X-20 Materials Research Program, served as the single most important database available in the U.S. At the time, Rockwell International initialed work leading up to the Space Shuttle. In total, few vehicles have contributed more to the science of high Mach flight, and even fewer have done so without ever having reached the actual hardware stage.
The true lifting body concept was developed in the late 1950s by Dr. Alfred J. Eggers Jr., Assistant R&D Director for Ames Aeronautical Laboratory, later NASA Ames Research Center, at Moffett Field, California. By slightly modifying the shape of a spacecraft's symmetrical nose cone, he found aerodynamic lift could be produced. The idea was further developed by aerospace engineer R. Dale Reed at NASA's Flight Research Center, FRC, later Dryden FRC, Edwards Air Force Base. Reed adopted the idea to create a spacecraft crew capsule that could land conventionally like an aircraft after atmospheric re-entry and be reused, unlike the crew capsules of the Mercury, Gemini, and Apollo space programs, which fell to Earth before deploying parachutes for a splashdown in the ocean. The form of a lifting body can be thought of as opposite that of a flying wing. While a flying wing has little or no fuselage, a lifting body is all fuselage and no wings, but with vertical stabilizers. Lift is generated by the broad fuselage shape during its glide through the atmosphere. In 1962, Dryden FRC began a program to build a lightweight, unpowered lifting body to flight test the wingless concept at low speeds. The resulting M2F1, MF stood for manned flight, dubbed the Flying Bathtub, made its first tentative flight tests the next year over Rogers Dry Lake. It was tethered by rope and towed at up to 200 kilometers per hour, or 110 knots, by a Pontiac convertible car, the same auto-tow method often favored for launching recreational gliders of the era. After several hundred ground tows, a NASA R-4D C-47 tow plane was used. 77 of those flight tests, made by 10 pilots including Chuck Yeager, proved the aerodynamic and handling qualities of the lifting body. Following studies conducted at its Ames and Langley research centers, NASA then designed successors to the lightweight M2F1, a pair of heavyweight lifting bodies. Designated M2F2 and HL-10, HL for horizontal landing, those vehicles were built by Northrop, which had earlier submitted a proposal for the Dyna-Soar program. The M2F2, flown during 1966-67, was the first of 5 heavyweight lifting bodies developed and flown by FRC. Although it was fitted with an XLR-11 rocket motor, its 16 flights were all glides from the B-52 mothership. In 1973, the M2F2 was seen in spectacular fashion on millions of television sets in America and around the world, though most viewers would not have known what it was. It was the subject of a 1967 archival crash landing film shown in the opening sequence for TV's $6 Million Man series, starring Lee Majors as USAF Colonel Steve Austin.
Westerly at about 10 knots. Coming on. I'm indicating 004. How does that look? Looks good, Steve, and all systems are okay here. The winds are westerly at 10 knots. Okay. This is NASA 1 calling 10 seconds now. 10 seconds, roger. 0, 5, 4, 3, 2, 1. We have separation. Inboard and outboard, they're on. We're coming forward with the side stick. Looks good. Roger. I've got a blowout. Day for 3. Get your pitch to 0. Pitches out. I can't hold it altitude. Correction. Alpha 4 is off. Track collected emergently. Flight call. I can't hold it. She's breaking up. She's breaking.
The M2F2 is shown tumbling numerous times after gliding into land. According to the show's premise, Austin survived the crash and was rebuilt as a bionic man. Its real pilot, NASA test pilot Bruce Peterson, was seriously injured but survived, although he disliked his terrifying accident being on public replay every week. Surprisingly, the M2F2 was not completely destroyed and was rebuilt as the M2F3, now with a third central fin for better lateral stability. It flew 26 more times between 1970 and 1972, achieving an altitude of 71,500 feet and speed of Mach 1.6. In 1962, the USAF Flight Dynamics Laboratory joined NASA in its interest in lifting body research and initiated a 3-phase program called Spacecraft Technology and Advanced Re-Entry Test. Phase 1, Asset, Aerothermodynamic Elastic Structural Systems Environmental Tests. Phase 2, Prime, Precision Re-Entry including Maneuvering Re-Entry. Phase 3, Pilot, Piloted Low-Speed Tests. The Martin Marietta Corporation had for several years been following Dr. Egger's lifting body research. The USAF contracted the firm to produce 4 examples of a small, 2-meter-long Phase 2 prime vehicle, the SV-5D, soon renamed X-23A. During 1966-67, 3 successful 30-minute space journeys were made, launched by Atlas rocket from Vandenberg Air Force Base. Using telemetry data and examination of the recovered vehicles, each flight explored the high-speed characteristics of maneuverable re-entry vehicles. Among other things, the X-23A tested materials to withstand the heat of atmospheric re-entry, an ablative resin underside shield, and a carbon phenolic nose cone. With ablative shielding, the outer layer is heated to a gas, which carries the heat away by convection. In 1959, the Project Mercury space capsule was successfully tested with an ablative shield of fiberglass bonded with a modified phenolic resin. The X-15 flown that year had a titanium internal structure and Inconel X, nickel-chromium alloy skin, also designed for re-entry temperatures. For the reusable space shuttle, in the 1970s, reinforced carbon tiles, for temperatures greater than 1,260 degrees Celsius, and silica ceramic tiles, for lower temperatures, were developed. The X-23A was guided via both onboard inertial and ground-based navigation systems. Following each flight, it was recovered mid-air by C-130 aircraft, or after parachuting into the ocean. The program was a major step forward in hypersonic re-entry space vehicle design, furthering several research fields: maneuverability both in space and in the atmosphere, heat dissipation using water to steam cooling, earlier intended for the X-20, and ablative heat shields. Martin Marietta's next development, the X-24A, was a manned, rocket-powered vehicle to explore the lifting body design's low-speed flight characteristics and controllability. It did not venture into space, and as it did not undergo atmospheric re-entry, aluminium sufficed for its structural material. Like the X-15, it was air-launched from the underwing pylon of NASA's NB-52B mothership. Control was via a hydraulically operated system of 10 control surfaces, the pilot receiving artificial field feedback to the control stick and rudder pedals. The craft was flown and landed at Edwards Air Force Base during 1969 to 71, before being radically altered with the addition of a long nose and flattened undersides and renamed the X-24B. A planned X-23C hypersonic craft did not eventuate. NASA's X-33 program of the 1990s called for a single-stage-to-orbit reusable launch vehicle and eventually a commercial passenger spaceliner for intercontinental travel. Submissions were received from McDonnell Douglas, Rockwell, and Skunk Works at Lockheed Martin. Lockheed Martin was the result of a 1995 merger of Martin Marietta and Lockheed. In 1996, Lockheed Martin's design was accepted for an uncrewed technology demonstrator for the company's suborbital VentureStar passenger spaceliner proposal. Like the X-15, the X-33 would rely on metallic thermal protection. The 21-meter craft was to lift off vertically and reach Mach 13, powered by a pair of 1,800 kilonewton aerospike rocket engines, which, unlike standard rocket engines, would maintain efficiency at a range of altitudes. But in 2001, after being 85% built, the X-33 and VentureStar were cancelled 5 years before operational debut was planned. NASA's X-38, similar in design but larger than the X-24A, was developed concurrently with the X-33 in the late 1990s. Unlike the X-33, however, it was completed and test-flown from the NB-52B mothership. The X-38, a joint NASA-European project, was to serve as an emergency crew return vehicle for the International Space Station and thus had to accommodate a complement of 7. 2 prototypes were built and flown atmospherically, while the Orbital prototype was only 90% completed before program cancellation in 2002. Nowadays, the Russian Soyuz crew transfer vehicle and the US SpaceX Crew Dragon spacecraft, which first delivered astronauts to the International Space Station in 2020, are available for space station emergencies. Other reusable spaceplane concepts with lifting body properties have included the Rockwell X-30, cancelled in 1993, while others, such as the Boeing X-48 UAV with a 6.4-meter span and flown in 2007, featured either blended wing body or flying wings designs. It is incredible to think that early German design concepts, only 30 to 40 years after the Wright brothers' first powered flight, would lay the groundwork and inspiration for American X-plane programs and the amazing vehicles they produced.
We stand forever at a point in time called now. The past we can only remember. At best, we can learn from it. The future we can only surmise. At best, we can try to shape it. Less than 5 hours from this point of now, John A. Mankey will find himself suspended 8 miles above the Mojave Desert. As test pilot for NASA's Flight Research Center, he will play out his role in shaping the future in a wingless craft that looks as though it has no right to fly. Three hours now. John Mankey has already flown an F-104 over the test range to check for turbulence and returned satisfied. In the nearby physiological van, a medical team is affixing tiny sensing devices to his body to transmit his physiological reactions during the flight to recorders at ground control. Since weeks before now, engineers and technicians have been checking and rechecking every fitting and instrument and connector in this lifting body called the HL-10. Finally, to fill its tanks with the alcohol and liquid oxygen that will, in little more than 2 hours, propel it for the first time faster than the speed of sound. Getting men into space is one problem. Getting them back is another one. They ride out on thundering names like Mercury and Gemini and Apollo. Batter their way back through the searing atmosphere at more than 17,000 miles per hour. And once through that barrier, ride parachutes to an ocean splashdown. For infrequent missions, a widespread recovery force of dozens of ships spread over hundreds of miles can be justified. But as more and more men are suited up to leave their world, as flights to and from orbiting space stations become more frequent, then easier, more flexible, less costly ways to let them return simply must be found. That's what John Mankey and the HL-10 and NASA and the Air Force are doing, making sure answers will be ready by the time they're needed. Less than 90 minutes from now, the flat-bodied craft will be carried 8 miles high beneath the wing of this B-52, there to be released as another step in the proof of a theory conceived almost 20 years ago at NASA's Ames Research Center. Up to the present, manned spacecraft have been cone-shaped, re-entering blunt end first, but they lack maneuverability. At first, it might seem reasonable to turn the vehicle around and re-enter with the pointed end forward. However, this shape would generate excessive heat, and more important, it still would not have the desired maneuverability. The first modification was to make its cone slender and blunt its nose, but it still could not fly well or be maneuvered. So the next modification was to slice the cone lengthwise. In effect, this reduces the pressure on the top, so that pressure on the bottom will dominate, providing more aerodynamic lift and greatly reducing drag. In theory, it should fly, but could it be maneuvered and landed? Ideally, a way was needed to bring down the half cone, much like a conventional airplane. For such a landing, the best shape is shallow and broad. By flattening and widening the half cone and adding aerodynamic surfaces for control, a configuration was evolved, a lifting body, capable both of high-speed re-entry and low-speed landing. Such a craft could act as a shuttle, carrying people and material from space stations back to Earth. From outer space, its pilot could maneuver it to touch down at a pre-selected landing site, or, if necessary, alter his course and land at a different location. Unlike the now familiar space capsule, the lifting body is reusable. Its initial cost could be spread over hundreds of flights, and the configuration lends itself to larger sizes, able to carry dozens, perhaps scores of passengers. But a child must crawl before he walks, and walk before he runs. In the lifting body program, crawling for John Mankey means countless hours in this simulator, up to 50 hours for each flight, while an analog computer interprets his every move and patiently plots out the reaction it would produce if he were airborne. And it means many dead-stick landings in an F-104, trimmed to approximate the lifting body's characteristics. Seven years earlier, the first full-scale flight test model crawled, literally, as an automobile towed it aloft at the end of a cable. Simple in construction and low in cost, it nevertheless did what the wind tunnel tests had said it would. It flew. Now it was time to walk. The DC-3 towed the lightweight steel and plywood lifting body and its pilot to altitudes up to 12,000 feet. There it was released and allowed to glide in free flight to the desert floor, to land at a speed of 80 miles per hour. This first test vehicle logged over 400 successful flights. But all that is the past for John Mankey. As with fellow test pilot Bill Dana, who will control this flight, he walks toward his future, less than 90 minutes from now, poised beneath the protective wing of the B-52. Mankey is a professional, long familiar with flight test procedure. That procedure is to increase the performance step by step until the craft has been pushed to its limits in terms of altitude and speed. Lifting bodies have flown before, of course, and many times. The first heavyweight configuration was called the M2F2. On a hot July day in 1966, another NASA test pilot, Milt Thompson, made the first glide flight. Even though developed from the earlier configuration, this was no plywood lightweight, but a fully equipped test vehicle weighing almost 3 tons and designed to touch down at over 200 miles per hour. The 8-mile drop took less than 4 minutes. One successful flight proved only that it could be done. Refinement, improvement, the evolution of an idea into a working system would have to come from many such flights. From hypersonic wind tunnel evaluation, and from constructing and testing a number of different designs. This lifting body, the HL-10, with 3 vertical stabilizers instead of 2, was developed at Langley Research Center. Less than 6 months after the initial M2F2 flight, the HL-10 took its first plunge to the desert, with NASA's Bruce Peterson at the controls. Then, shortly after launch, trouble. Problems with the controls. Next, a strange high-speed buffeting the wind tunnel tests had failed to disclose. Peterson could have ejected, but he still had control of his craft and chose to ride it out as the ground reached up for him at more than 200 miles per hour. Like what pilots would call a piece of cake. It always does after someone has done it and the moment has been frozen on film. Can John Mankey, now less than an hour from takeoff, put from his mind another moment? A long moment that began a year before when Bruce Peterson again dropped away from the mothership in the M2F2. A moment that continued as violent oscillations suddenly struck the craft near the ground. The pilot managed to recover, but too much precious time and altitude had been lost. The moment ended. Miraculously, the man survived. So did the airframe, to be rebuilt for future flights. But for John Mankey, This is now. Sealed in his own tiny world, he has too much ahead of him to reflect on the past. He knows the control problems have long been corrected, and in 45 minutes, and what will be only its fourth rocket-powered flight, he will push the HL-10 through the sound barrier of Mach 1, up to 724 miles per hour. The lifting body has proved over and over that it can maneuver and land, but wind tunnel tests have never shown exactly what will happen as it exceeds the speed of sound. Only when its rocket engines kick it through that critical barrier will they and John Mankey be sure. The test will be labeled a success, though of course he can't know that yet. To the scientists whose speculation made it conceivable, to the engineers and technicians who made it possible, to John Mankey, whose life depends on all of them and his own skill besides, this is the successful completion of another milestone. But in a broader sense, it is just a test. Another step in the evolution of an idea. Future flights will go higher, up to the fringe of the atmosphere, and return at speeds well above the speed of sound. In the now that will be with us tomorrow, a lifting body may return men and women from space, much as commercial jets land today. Or from this work, some new, as yet unthought of configuration may emerge. For the moment always with us called now, always changes.